I'm going to talk to you about mixing and its importance in bioreactions. And I'm not going to focus specifically on biotechnology. I'm going to broaden the scope out a bit because a lot of the mixing problems that you encounter, they're not any different in one biological system like a beer fermentation, for instance, than they are in a biopharmaceutical reactor. So I'm going to talk to you about things that doesn't relate to pharma, but which I still think could be important in pharma. Pierre already introduced me, so I'm not going to spend any time on this. I would, however, like to say just a few words about Alfa Laval tank equipment where I work. So we basically sell tank equipment components, and that would primarily be tank cleaning equipment. Then we have a mixing portfolio that consists of agitators, what's known as rotary jet mixers and magnetic mixers. Then we sell instrumentation, tank covers and tank accessories. But as Pierre already said, my area of expertise is kind of mixing in general. So here you see the agenda of my talk. I'm going to start out by talking to you about what kind of mixing duties are actually important when we consider bioreactions. Then I'm going to tell you about what will happen if you have poor mixing, and I'm going to illustrate that by a number of examples drawn from my own work. So that's also one of the reasons why I'm not only talking about bioindustrial fermentation and cell culture. And then I'll talk about what you should consider when you design an agitator for a bioreactor. And then if we have time, then I'll go a little bit into magnetic mixer design also. So the reason why mixing is important in bioreaction systems is basically to ensure that we keep the cells in suspension. That, of course, we need to do. Then it's to ensure that we have adequate blending of substrates that we are introducing during the process, adequately fast pH adjustment, etc. If we're introducing gases, we utilize the mixing equipment to enhance the mass transfer. If we need to do heat transfer, then the mixing will aid convection and thereby heat transfer. And ultimately, we basically do this to promote the biological reactions taking place. So if we just look at the economic impact of poor mixing in general, then it's been estimated around 20 years ago that the impact of poor mixing on industrial applications in the US in general across all industries was around 1 to 10 billion US dollars per year. And of course also, if you don't have optimal yield, then you need to do more downstream processing. So, but let me start out by giving you one example of what poor mixing can lead to. And this is an example of inadequate cell dispersion, and it's taken from the brewing industry. So we're considering mixing in beer fermentation here, probably the oldest biotechnological reaction that you can think about. So if you look at how lager is manufactured commercially today, it's done in batch reactors using vertical cylindriconical fermenters without having any mechanical agitation in them. And we're talking tanks that are maybe 100 to 600 cubic meter scale. Typically you're using what's called high gravity worts. So that would be worts that you ferment that have a very high sugar content, and the typical fermentation temperature is maybe 12 to 20 centigrades. You apply cooling by having internal jackets on the tank. And the underlying assumption here is that convection currents due to temperature differences between the cooling jackets and the beer, and the effect of rising CO2 bubbles that you'll get when the yeast converts sugar into ethanol and CO2, that will ensure good mixing. So you don't need an external agitator. That's been the general thinking. And it's been assumed that good mixing ensures homogeneity of temperature and the yeast concentration. And then the final assumption has been that when the yeast is exhausted, when the sugar is exhausted, the yeast will sediment out to the bottom, and you can take out the yeast before you transfer the beer to the filter line, or to a storage tank and then to a filter line. So some years ago, a guy called Chris Bolton from the brewing company Coors, he actually looked into how yeast was distributed instead of just assuming that it was distributed in a certain way. And he presented that at 2 European Brewing Convention congresses. And he used what's called an Aber instrument to measure the concentration of viable yeast cells. He put these instruments into waterproofed enclosures and he immersed them into the tank. So here you see his experimental system. This was done in full scale. He put in a number of these. So you can see they're sitting here. And just to give you an idea, here they are mounting them on a wire. And they look like this. This is the waterproof enclosure. Here you have the sensor. And then they put them in so that they were sitting here. So he can basically measure the yeast concentration at a lot of different positions in this tank. Here again, the probe location. The tank was a 1,636 hectoliter working volume tank. Brewers like to work in hectoliters, but it's basically 163.6 cubic meter. What you see in this graph is this one shows the sugar evolution in the sugar concentration in the medium versus time. Brewers like to record this in terms of present gravity. They basically just measure the density, and they can correlate that with the sugar concentration. And what you see here is the viable yeast cell concentration measured at this upper probe in the tank. So this one, or the yellow curve here, is for the next probe. The red one, we go further down, and now we get into the cone. Now you can see something happening. So what you can see here is initially in the fermentation, the yeast is actually not very well distributed. And that's because you haven't started formation of a lot of CO2 yet that will provide the mixing needed in this reaction. And then when approximately 60% of the sugar has been consumed, the yeast actually starts to settle out in the cone. If you have all the yeast sitting as a compact mass down in the cone, it's not going to do you a lot of good, because you'll have all kind of mass transfer issues into that sediment to actually convert the sugar into alcohol. So one way of actually getting around this would of course be to install some kind of mechanical mixing system. And you can use agitators for that, but they've been used very little in the beer industry or the brewing industry, because they are not considered, at least by brewer, as very sanitary. Instead, a system called the Isomix system is currently being installed in a number of major brewing groups. And this system is basically based on mixing by rotary jet mixers that are modified Alfa Laval rotary jet heads that maybe some of you or most of you know from CIP. So the principle behind this system is that you take the fermenting beer, you recirculate it via an external pump, and then you re-inject it into the bulk liquid via one of these rotary jet mixers. You can add different things in the loop if you want to. They don't do that in the brewing industry. If you want to remove heat, you can do that in a plate heat exchanger that you introduce in the loop. And basically the mixer can be installed either from the top or the bottom. If you install it from the top, it can also be used for CIP, basically because that was the original purpose of the machine. So I just want to illustrate the function to you here. What you see here is a transparent tank. it's filled with water that contains iodine and starch. So when you add those two components together, they form this black complex. If you then add a component called thiosulfate, thiosulfate will reduce the iodine to iodide and it turns colorless. So you can actually use this kind of system to visualize mixing. So I'm just going to show you what the system operates like. So there the thiosulfate is injected and you can see how the liquid is decolorized. But you can also see how the head operates. It actually doesn't turn very fast. The mixing action is provided by liquid jets leaving these 4 nozzles at a pretty high velocity. That's what gives you the mixing. But because the jets are rotating, you're actually covering the entire vessel. What you see here is the effect that we've seen in different breweries after installing this system. So this is the reduction in process time for different breweries, and you can see that we've seen reductions in process time of everywhere from 15% up to more than 40% by installing this system. So this is basically something where we get a faster process just because we keep the cells in suspension instead of just letting them sit at the bottom of the tank for an elevated period of time. Okay, the next example that I want to show you is an example of inadequate liquid phase blending. And the model system that I'm going to discuss is enzymatic oxidation of lactobionic acid. And it was a system that I worked with when I did my PhD. And I thought I should be doing a lot of enzyme kinetics, and I did. But it ended up being more of a mixing study also, because we saw some really strange effects, or at least we couldn't explain them initially. Anyway, lactobionic acid, just to give you some kind of background about that, it's actually used in organ transplantation and calcium supplements, cosmetics. Right now, it has other applications. It could be used as a co-builder in detergents, as a corrosion protection. In food technology, it can be used in a acidulant, a filler in cheese production, and in functional drinks to supplement calcium. The reaction of producing lactobionic acid from lactose is shown here. So you have an enzyme that you call a lactose oxidase, and it oxidizes lactose into a lactone that's broken down into lactobionic acid. A byproduct is hydrogen peroxide. So you need to add catalase, because otherwise the hydrogen peroxide will basically kill your enzyme activity. So you need to add the lactose oxidase, and you need to add catalase. So we started that in pretty small scale. All our experiments were done in a 1 liter bioreactor. We kept the dissolved oxygen tension constant using feedback regulation of 2 mass flow controllers that dispersed respectively air and nitrogen. So we kept the very same oxygen concentration throughout the reaction. pH was kept constant at 6.4 by addition of 2 molar sodium hydroxide base. But we had buffer in there. So when you looked at the pH meter, every time a drop of base went in, the pH would go down to maybe 6 point, or every time pH dropped to 6.39, it would add a drop, it would go up to 6.40. You couldn't see any oscillations whatsoever on the pH meter. But what we saw when we started this reaction was that we had a declining rate in reaction. It declined very fast with time, the rate in reaction. And then we started looking at what happened when we increased the oxygen concentration. And we found out that the rate increased, the initial rate increased when we increased the oxygen concentration. But the rate of deactivation also went up quite a lot. So we speculated, could this basically be because when the rate goes up, we put in more alkali. If we don't have perfect mixing, that alkali can destroy the enzyme, so that gives us faster deactivation. And actually that turned out to be exactly the case. So if we switch from 2 molar sodium hydroxide to a weak base, ammonia, that deactivation pattern, it just disappeared completely. And that basically proved that mixing was very important in this system. So the enzyme deactivated when we used 2 molar sodium hydroxide for neutralization. Even though we were doing this at really small scale, we're talking 1 liter reactor. We had 2 Ruston turbines in there that were revolving at 1000 RPM. I mean, it was mixing really, really fast. Every time you put in a drop of sodium hydroxide, you couldn't see any change on the pH meter whatsoever. You didn't have any oscillations or something. So this was just because you had a very small zone with a higher local pH value for a very small amount of time. And I mean, that would be something that you could see in other biological systems also. So if you, for instance, go to cell culture, you can have the same situation if you have gradients in pH due to poor mixing. Because often in cell culture, you don't have a very vigorous mix, right? You want a gentle mix. So you can actually, in some situations, get fluctuations in pH, which can lead to a lower yield. If we go from these two into industrial aerobic fermentation, then I just have a picture here of a typical industrial fermenter. You can see you have a lot of internals in here. You have some cooling coils here to remove heat. Then you have an agitator shaft here fitted with 2 Ruston impellers. Ruston impellers, they've been used quite a lot in industrial fermentation. And then you have baffles in the tank to break up the vortices that would otherwise result. If you don't have baffles, you'll get a vortex. So if we look at typical aerobic fermentations, then if we consider yeast as an example, yeast fermentation, where the purpose is to produce yeast or to produce a product that's captured in the yeast. That could, for instance, be insulin, if you look at the way Novo Nordisk makes insulin. Then you really want to keep the sugar concentration homogeneous, and you want to keep it low, because if you don't keep the sugar concentration low, the yeast will start to produce alcohol. And you don't want to make beer here, you want to make yeast. You want to ensure a constant pH. You want to ensure sufficient oxygen transfer by adequate air dispersion. And when we are talking aerobic fermentation, you need a lot of oxygen transfer. So in a typical industrial scale bioreaction of where you're maybe producing yeast, you might be producing some enzyme in filamentous fungi. It could be an E. coli fermentation. Typical aeration rates will be on the order of maybe 1 volume of gas per volume of fermentation volume per minute. So we're talking huge amounts of air that you need to introduce. You need to be able to break that air up with the agitator. Otherwise, you're not going to get good mass transfer, and you're not going to get the process result that you're after. Also, if you have these very aerobic fermentations, they will generate a lot of heat. So you also need to make sure that you can actually remove that heat. So by having good mixing, if you have the coils in the tank, you will get better heat transfer, basically. So what I'm going to do now is I'm going to introduce you to how you would actually, or what to consider when you actually select an agitator for perhaps an aerobic, highly aerobic fermentation. So here's just a small schematic of an agitator. So you have a motor with a gearbox, and then you have an agitator shaft and an impeller at the bottom. You could have multiple impellers also. And you can see in this tank you have baffles. You can have different agitator types. You can have top-mounted agitators. They would be would be what you would normally put into a fermentation tank. Or actually that would be a top-mounted agitator with bottom support. You can have bottom-mounted agitators and you can have side-mounted agitators. These guys here are typically not used in industrial fermentation. You would typically need a top-mounted agitator with bottom support. We talked about baffles a little bit already, but the reason why you're actually introducing baffles is to prevent the vortex formation that would otherwise result. If you don't have the baffles and if you are having the impeller placed centrically in the tank, what would happen is that the liquid will basically just go around like this. You'll get a vortex, but you won't get good mixing. I mean, it's just fluid elements traveling around, so you need the baffles to get really good mixing. Then if we look at the impeller types that you can use what's called radial flow impellers, you can use what's called axial flow impellers, and then you can use something called closed clearance impellers. But these ones are impellers that are typically used for high viscous products, so we don't want to consider them here because even high viscous industrial fermentations, like if you're having an industrial fermentation of filamentous fungi, I mean, you won't use these ones. You'll use these kind of impellers. And just to give you an idea about what the difference is, then radial flow impellers, they basically produce a radial flow. They're primarily used with low viscosity liquids in baffle tanks. And the disc turbines of them are normally used for gas dispersion. So here you see a number of different radial flow impellers. The Ruston turbine has been used quite a lot in industrial fermentation, but people tend to move from this type maybe over to this type now. I'll come back to why. Here you see a picture where you can actually see the flow pattern made by a radial flow impeller. So it sends out flow radial, and then part of the flow is diverted down like this, and part of the flow goes like this. So you have two circulation loops. The other type of impellers are called axial flow impellers. So they pump primarily, but not exclusively, vertically, either upwards or downwards, depending on basically whether or not you put the impeller like that, or whether or not you put it upside down and take the shaft in the opposite direction. They're used mainly in low to medium viscosity liquids, I should say low to medium viscosity. Yeah. They're typically used so they pump downwards, but as I say, you can actually use them in up pumping mode. For instance, if you want to disperse gas. And they produce a flow pattern like this, so flow is diverted down and then it goes all the way up and then down, so you only have one circulation loop. When we consider impellers, there are basically two numbers that are very important. The first one is the Reynolds number. It says something about the ratio of inertial forces to viscous forces, and whether or not the flow is turbulent, transitional, or laminar. And you need to know that, because mixing, when you design an impeller, you'll have different functionalities for how long it takes to mix, whether or not the flow is actually turbulent or transitional. Another very important number is called the power number. So it relates the power input to the stirrer speed and impeller diameter. And there are several reasons why it's important, but one of them is that if you have an impeller with a high power number, that means that you have a large torque. So it means that if you choose such an impeller, you also have to size your shaft and gearbox, etc., so it becomes more expensive. And here are some power numbers for different impellers. So you can see that Ruston impeller we talked about before, it has a very high power number. So that means that if you take a Ruston turbine, it will revolve at pretty slow speed, but it will draw a large torque. Then you can have other impellers like, for instance, this one here that's called a Lightning A315. That's a hydrofoil impeller like this one. It has a very low power number, so it means that to dissipate the same power, it needs to revolve faster, but it doesn't require as much torque, so you can make a cheaper construction. So if we look at our agitators in Alfa Laval, our agitators are primarily hydrofoil impellers, or based on hydrofoil impellers. They have they're very good at pumping. So if you compare something called a pumping number, which basically says something about how good is the impeller at pumping or making flow compared to the power number, so that would be something about how much power is it consuming. It has a very high ratio of 2.6, and common for other types is maybe 0.6. So this basically means that with such an impeller like this one, you can make a lot of pumping at low energy consumption compared to other impellers of the same diameter operated at the same rotational speed. So if you have a process where you need a lot of flow, I mean, you should go for this kind of agitator. If we look at mixing time, then mixing time can be important, as we already discussed, because, for instance, if you are blending in substrate in a reaction where you need to have a sufficiently low substrate concentration all the time, because otherwise your organism might start producing ethanol if we are talking yeast. It might start producing acetate if we are talking E. coli. Or it could be that if we are having filamentous fungi or enzyme production in filamentous fungi, they'll just shut down the enzyme production if you don't have that low substrate concentration all the time. To get that low substrate concentration, you need to have an adequately low mixing time. So therefore, it's important to actually study this mixing time. If you look at a system with a single impeller in a tank with the diameter equal to the height, that's what this basically says. This is the height, this is the diameter, and we are operating in the turbulent regime, then the mixing time can just be written as a constant times the power divided by the unit mass raised to a certain exponent times the tank diameter raised to the power of 2/3 times the impeller diameter divided by the tank diameter raised to the power of -1/3. This equation basically says that if you put in two impellers that have the same diameter and that they are operated at the same power input, it doesn't matter what the impeller looks like. It's going to produce exactly the same mixing time. So then you might argue, why am I standing here talking about this? Because now I'm coming to the conclusion that you can put in whatever and it doesn't matter. But it is actually not unimportant, because as I told you before, if you choose an impeller with low power number, like for instance that interfoil impeller, it will be much cheaper to install than an impeller of the same diameter where you have the same power per unit volume that has a higher power number. So it's still important to think about, not because it'll give you a different process result, but because it'll be much, much cheaper to install. Also, what you can do is that if you say that you want to operate at the same torque, what you can do is you can actually install an impeller like the interfoil impeller that has a low power number with a much larger diameter before you get to the same torque as a impeller with a high power number that has a smaller diameter. And you can see here that the diameter of the impeller is actually in the equation, so that if you do that, you will get faster mixing. The equation actually also say that if you scale up at constant power input, and that it's done, at least in some industries, that you say, now we transfer from, I don't know, 10 meter cube to 100 meter cube. How should we do that scale up? We probably keep the specific power input constant. If you actually do that, then your mixing time will increase with the tank diameter raised to the power of 2/3. So mixing problems definitely become worse on scale up. So you have to think about that what you go in and do in the lab or in small pilot scale, it's not necessarily the same things that you're going to see on the large scale. So you really have to pay attention during scale up. Now, these were just vessels that look a little bit like me, so small and bulky, aspect ratio of around 1. If you take tall tanks, then it does matter quite a lot what kind of impeller you put in. So if you put these radial flow impellers in, so several radial flow impellers on top of one another, then they will produce something called zoning. So zoning is basically a situation where those loops that I told you, that I showed you here, imagine that you have a tall tank and you have another one of these impellers sitting up here. So zoning is a situation where that loop that this impeller generates is not going to get intimate contact to the lower loop that the impeller that would be sitting up here is providing. So it means that if you drop in some feed from the top, it will get pretty fast mixed in at the top impeller, but it will take a long time for it to be exchanged down to this zone so that it can be mixed into the lower part of the tank. If you take those axial flow impellers instead and have multiple of those stacked on top of one another, zoning is much less severe. So if you have tall tanks with more than one impeller and mixing time is of importance, then mixing time will be lower if you use axial flow impellers like for instance, our interfoil impeller rather than radial flow impellers. So if you remember that bioreactor I showed you in the very beginning, it had 2 Bruston turbines on top of one another. It's not going to give you very good liquid mixing. It's actually pretty slow in making an even concentration in whatever substrate you put in on the top. If you want faster mixing, you need to go in and retrofit on that agitator. Then if we look at gas dispersion, which is very important also in aerobic industrial fermentation, then there are some concepts there also. So the first concept is the transition from what is called flooded to loaded. So flooded is a situation where you're basically, either you're providing too much gas that the impeller can handle, or you're operating the impeller too slow so it can't handle the gas. So it's a situation where, you know, the bubbles pretty much just rise up. They're not well distributed in the tank. This is loaded. That's a situation where now they're actually well distributed, at least above the impeller, and here they're completely dispersed in the entire volume. So studying this transition from flooded to loaded, it's important because it tells you how much gas can the impeller handle before it kind of runs out of speed. Because if you get to a situation like this, then mass transfer is going to be really bad. So you're just putting in a lot of air that's not going to do you any good. Another important concept is what happens with the power on the motor when you start gassing. Because some impellers will actually take up less power. So that means that unless you're running the motor on a variable frequency drive, you're not actually getting all the power out of that impeller that you want to get out of the impeller. So it's best if the power number remains constant when you start actually adding gas. So If we look at gas dispersion, then radial flow impellers, they've traditionally been used. And that's also the reason why you saw those kind of impellers in that industrial bioreactor I showed you before. They're very good at dispersing gas. The Roston was the preferred choice. But it has the disadvantage that the power, if you operate it at a constant speed and start adding gas to it, the power actually decreases upon gassing. If you take one like this, power doesn't increase when you start adding gas. It just stays constant. So that means that you can do basically the sizing once and for all, and you know how much power it's going to draw. And then it can actually handle much more gas also before it floods that situation where the gas wasn't very well distributed. So I would definitely choose an impeller like this for any gas dispersion task rather than an impeller like this. You can, however, also use axial flow impellers, but you need to operate them in a mode so they're pumping upwards. If you try to take an axial flow impeller and start gassing it and it's pumping downwards, then, I mean, you all know gas wants to go upwards. The impeller wants to pump downwards. So what's going to happen is that you're going to get a lot of instabilities. You're going to get a lot of torque fluctuations on the shaft and the gearbox. So from a mechanical point of view, it's just not good. And I've heard stories about, I think it was Merck that did some trials where they wanted to test a downpumping axial flow impeller in their pilot plant. And the torque fluctuations were so big that the fermenter, it actually pulled itself out of its grounding and it kind of started dancing through the room. So you don't want to take an axial flow impeller and make it pump downwards. So just some recommendations on what impellers you should actually choose then. First of all, if we are talking mixing in those small bulky tanks that have a height equal to the diameter and we don't consider gas dispersion, then choose a low power number impeller, like for instance the Interfoil impeller. If we are talking mixing in tall tanks but without gas dispersion, then choose axial flow impellers because they don't give you this zoning. You can choose either up pumpers or down pumpers, it doesn't really matter. If we're talking applications where both mixing and gas dispersion is of importance in tall tanks, like for instance in industrial fermentation, then you should probably use a modern radial flow impeller as the lower impeller for gas dispersion, and then some axial flow impellers as the upper impellers to provide good liquid mixing. Okay, now I just want to talk a little bit about cell culture. And the reason why I don't talk about cell culture before now was that I wanted to kind of introduce those concepts for agitators before getting to cell culture. So cell cultures, or animal and insect cell culture, is basically used in the production of highly valuable biologicals such as vaccines, hormones, growth factors, and maybe monoclonal antibodies. The cells, they lack a cell wall. If you compare it to, for instance, aerobic fermentation, the oxygen transfer requirement is very low compared to if you have aerobic fermentation of, say, bacteria, yeast, or filamentous fungi. So you don't need to transfer that much air. However, the dissolved CO2 concentration has to be controlled because too high values will lead to toxicity to the cells. So, if you study cell culture a bit, you will find out that people are very worried about shear stress because of that lack of cell wall. So these are systems that were at least originally thought to be very shear sensitive. And that has led to a situation where people in general employ very gentle agitation. However, nowadays it's been realized that the bubble liquid cell regions are probably actually more important And then if you take a system where you don't introduce gas into the system and agitate, you can actually agitate them at fairly high power inputs without destroying the cells. But this bubble liquid cell interface, that's very important. And you can basically break that up into 4 parts. You'll have bubble formations at a sparger. Then the bubbles, they can coalesce. They can also break up in the vicinity of the impeller. They will rise up the liquid. And at the very end, they will burst at the surface. And it's actually that bubble bursting which is a major issue. Because if you look at how much energy is released when a bubble bursts, it might sound totally counterintuitive. But nonetheless, if you look at bubble bursting at the surface, it releases a very high local energy level. It's only local, of 0.5 kilowatt per milliliter. So if you have a cell, that rises up in that bubble liquid interface and it reaches the surface, then that cell will be exposed to that high energy level, and it can't handle that. So bubble sizes below 5 millimeters are considered to be the most lethal ones, and for this very reason, you will add different surfactants when you do cell culturing. So you'll, for instance, add the surfactant chloronic F68 that gives a protective effect. If you look in the literature, there are several suggestions for why it gives a protective effect, and they're probably all, valid, and they just give a cumulative effect. Some studies suggest protective effect due to incorporation in the cell membranes, but also the bubble surface properties of those bubbles are altered, and less cells actually adhere to the bubble surface. So you have less cells transferring to the top where the bubbles burst. So another thing that you have to consider in cell culture is that if you're adjusting pH with alkali, then that can actually give you pretty big excursions in pH if you have too little mixing in there. And there will probably, or there at least has been systems with too little mixing because people have thought that the cells were so sensitive to mixing. So if you look, for instance, at some work done in 8,000 liter scale using a small diameter Ruston turbine revolving at 60 RPM at pretty typical energy inputs in cell culture, then if you just dipped in alkali to adjust pH on the surface, then that actually gave you pH excursions of 0.8 pH units, and that can give you lowered cell viability, and it can impede product formation. So you can actually get better liquid blending if you dissipate the same amount of energy by using one of those large diameter hydrofoil impellers. So, if you have a situation like this, you might want to be thinking about not using a Ruston, but using a hydrofoil instead. The fastest mixing, however, and therefore the least excursions in pH, you'll get if you add the feeding point very close to the impeller region by installing a dip pipe. It's often not used because it's considered hard to clean, but you can clean it if you just put in 2 tank cleaning machines so that you don't have a shadow that they can't handle. So it's not impossible, and it does give you very fast mixing so that you don't get these pH excursions. If we look at the CO2 toxicity, then as I already said, we need to control the dissolved CO2 concentration, because CO2 in too high concentration can be toxic to the cells. The CO2 concentration that's dissolved will depend on what amount of partial pressure of CO2 you have in the gas bubbles. So therefore it's important to have a certain gas flow rate so that you have a sufficiently small partial pressure of CO2 in those gas bubbles. So one strategy that's probably not really applied that much in practice, but one strategy could be actually to introduce two sparges. One that produced fairly big bubbles so that they could help you drive out the CO2, and another one that produced small bubbles that actually gave you the transfer of oxygen into the medium that you need. So just to conclude on this, I have a suggested design here, and it's not something that I came up with. I have it from a very good reference book that covers mixing in industrial fermentation. That if you're interested in this topic, it's a fantastic reference from a chapter called Mixing in Fermentation and Cell Culture. But what these guys propose, and the two first authors here, they used to work with Merck. Then they proposed that in tall bioreactors you should use a modern radial flow impeller as the lower impeller for gas dispersion, and then you should combine it with an axial flow hydrofoil as the upper impellers to provide good liquid mixing. And you should operate at sufficient intensity to provide good liquid mixing. I mean, you can't operate at too little intensity either. That will also not be good for the cells. The design should avoid pH excursions, and subsurface addition pipes would be most efficient, but you need to consider CIP. Oxygenation requirements should be coupled to CO2 ventilation rates. You should try to keep the bubbles above 5 millimeter in size, but in practice that can be very difficult to control. And then you should use some kind of surfactant like pluronic at a rate of at least 0.5 grams per liter. And I think my time is about to run out. I do have a section here about magnetic mixer, a really short section, but if any of you are interested in the magnetic mixers, we have one on display out there, and I mean you can just come by and then we can talk magnetic mixers if you want to talk magnetic mixers. But they are, just to give you 3 keywords, they are typically used in batch sizes that are not that big. You don't have a mechanical seal through the tank wall like you do with an agitator. They can be used in cell culture, but are often used in the downstream processes rather than in the actual cell culture. So with this, I would like to thank you all for your attention, and I'm happy to ask any questions you may have.
Maybe your first one regarding the magnetic mixer. You say that it's more for the smaller tanks. If you have maybe a larger tank, you can also put 2 above each other.
I mean, at least our design is made in such a way that it's actually welded into the bottom of the tank. So there is no way that I can, introduce one higher up, like I would be able to if we were talking agitators, for instance, where I could have several side entry agitators sitting in a tall tank.
Mm-hmm. So it's a little bit different as you have the side-mounted agitators. Is it different if you use the side-mounted agitators instead of magnetic mixers above each other? Because you can use 2 of.
Yeah, but it's because of the construction. I can't install it like this. If it's I can't install it so it's kind of sitting sideways, if you know what I mean.
Mm-hmm.
It has to be sitting like this.
Okay.
Does that answer the question?
Yes.
But the primary reason why you can't go up in size above a certain size is because the entire device is controlled by magnets, right? Mm-hmm. So if I have let's say I have a very large tank, 100 meter cube, something like that, which is not uncommon in industrial fermentation, then I would need a very large impeller to actually handle that. And I would have a very hard time actually building a design with suitable bearings and suitable magnets that could actually do that. So that's where the limitations are in terms of what volumes you can handle with magnetic mixer.
What's the difference between the first system you propose, so the rotating system, and the impeller system? What's the difference? Is the viscosity of the product?
Pardon?
The difference, you propose two type of mixing system. The propeller, or the first system you propose is
Isolation.
Okay, yeah.
What's the difference? How I can choose one system or the other system? Is the viscosity, I suppose?
I would say if you take the isomix system, we've used that up to 5,000 centipoise or something like that. So you can use that in fairly viscous applications also. The way we approach this is a little bit that we look at the process that a customer has. And then let's say you have a situation where you want to have really fast mixing, which the rotary jet mixers will provide, but it's also a design where you need to do CIP. Then often we can design it in such a way that you can use the same device to provide fast mixing and to use the same device afterwards for the CIP duty. Then that might be more cost efficient than an impeller solution. So at the end of the day, what we recommend, it boils down to looking at the individual application and then finding out what is the most cost efficient here. And there are areas that we never do with agitators, like for instance, we don't go into beer fermentation with agitators, we exclusively use the isomix systems. There are areas where the isomix system is too expensive compared to agitators. For instance, if you have a milk silo tank, now I know that I'm going into applications that are not anywhere related to pharma, but let's say then that you have a very simple storage tank. It could be milk, it could be whatever. Then a simple side entry agitator that's pretty cost effective would be the choice. You don't want to go for something like the rotary jet mixers that can provide you with very fast mixing because you don't really need it.
When you have two mixers above each other, you have zoning in the middle approximately. But for example, when you have an axial mixer and you're pumping up or pumping down, you have also a kind of zoning at the bottom of your reactor. How can you prevent from having this zoning? At the middle of the reactor, you can prevent by, for example, using baffles into your reactor. But how can you make it more efficient, that you're mixing more efficient without having that zoning in the middle at the bottom of your reactor?
You say in the middle and the bottom.
Yeah.
I mean, you are going to have some zoning. There is no way around, not getting any zoning. The point is basically just that it's much less severe than it is with radial flow impellers, because there it's really severe. If you look at studies that compared them like 1-to-1, you will see that that if you operate one system with, say, multiple Ruston turbines, and compare that to multiple axial flow impellers, and you do it at this, you put in exactly the same amount of power and everything, then the mixing time is probably twice in the radial flow impeller system compared to the axial flow impeller system. But you are going to have a certain amount of zoning. I would say if you want to get out of that zoning problem, what you really should do is that you should consider just taking 2 dip pipes. But a lot of people just don't like the idea about subsurface additions from a sanitary point of view. They like just to put in substrate on the surface and then keep their fingers crossed that the impellers can, distribute that fast enough. But you would get very fast mixing with, for instance, radial flow impellers if you were just prepared to have 2 dip pipes, one for each of the zones. And then you don't have to consider the zoning at all.
One question?
Well, I think if you use agitators, the propeller type of propeller is also depending on the shape of the tank. And if you have a tank with a very high angle, for example 20 or 25 degrees, what kind of propeller do you propose?
You mean if you have a cylindrical tank, basically?
More like an angle.
It's a good question, because if you look into the literature, then people always use model systems to study something like this, and they always use a disc bottom. Because you say that you need a disc bottom to have, optimal operation of an impeller, because the disc bottom will provide you with something where the currents can go down and then go upwards, and that's pretty difficult if you have a bottom looking like this. So,
or more like this, like an angle.
Yeah. I would probably tend to have something that was actually, that would be a situation where I would personally begin to look at, maybe a bottom mounted one that was pumping upwards, right? Because then it's pumping upwards, it's making a loop at the top, and then it's going back down. But it's not something that's well studied, so I can't really back it up by a lot of hard facts. It's funny, if you look in the literature, the 99.9% of everything has been made with baffle tanks, centrically mounted agitators in tanks of an aspect ratio of 1. And then if you go out in the industry and you look at the industry, I mean, you do find a few of those, but not very many. So.
Okay, thank you, Michael. I think it's time